Right, hello there. So today I will be talking about representation and stability analysis of partial differential equations, and in particular focusing on nonlinear PDEs. So PDEs are used to model a variety of physical processes that evolve in both space and time, such as fluid flow, or vibrations in mechanical structure, or the growth of a population in some fixed area, to name just a few applications. Now, these PDEs then relate the temporal derivative of some state variable of interest to its spatial derivative. So, for example, to model the flow between two plates under some simplifying assumptions, we can use this simple linear 1D PDE here, relating the temporal derivative of the flow velocity to its second order spatial derivative. Now, note that these PDEs will also be complemented by a set of boundary conditions. So, for example, we say here that the velocity at the lower plate must be equal to zero, and the velocity at the upper plate must be equal to the velocity of the upper plate, which we say is W here. Now, these PDEs then offer a simplified representation of this physical system, which we can then use to infer properties of the system, as well as perhaps design controllers. So the problem that we are interested in then is that of developing these tools for stability analysis, simulation, and control, as well as a variety of other problems for these partial differential equations. And in particular, we want these tools to be universal, meaning that they apply to any PDE within at least some particular class. And we want these tools to be automatable, so that a computer can do most of the hard work for us. Now, to illustrate what I mean with such a universal and automatable framework, let us first consider an ordinary differential equation, or ODE. So for ODEs, of course, to test stability, we can look for a Lyapunov function. So a function v, which is positive definite, or which decreases along solutions to the system. And if there exists such a function v, that means that the level sets of this function, for example, v is equal to 1 here, once a solution enters such a level set, it will remain in that level set for all future times, thus proving a notion of stability of the system. Now, finding such a Lyapunov function in general is non-trivial. If we restrict our attention to just linear ODEs, so that the vector field is defined by a matrix A, then we can parameterize a quadratic Lyapunov function by a matrix P, and then the derivative of this Lyapunov function along the vector field will also be quadratic and defined by a matrix Q. So then to test for existence of a Lyapunov function, and thus test stability of the system, we can look for a positive definite matrix P, such that this matrix Q here is negative semi-definite. And these are just linear matrix inequalities or LMI constraints, which we can solve using interior point methods. So in this manner, we have a framework for stability analysis of linear ODEs, and this framework is universal. It applies to any linear ODE, and it is automatable. All we have to do is specify the matrix A defining the vector field, and a computer can basically do the rest. Moving now to partial differential equations, if we consider just linear PDEs, we can represent them in a somewhat similar format, now using an operator A rather than a matrix A. Now note also that the state u at each time t is now still a function of space. And more than that, it has to be differentiable up to some order n with respect to the spatial variable. In addition, the state at each time has to satisfy a set of boundary conditions defining this space x here. So for example, if we consider our flow model from the first plate, we can represent the operator A here will become this second order spatial differential operator, and the set x here is defined by those second order differentiable functions satisfying our boundary conditions at the lower and the boundaries. Now, given this linear representation of our PDE, we can still test stability by looking for a quadratic Lyapunov function, where in this case, such a quadratic function will be given by the L2 inner product and parameterized by some operator P rather than just a matrix P. And then the derivative of this Lyapunov function along the vector field will again be quadratic with respect to the L2 inner product and defined by some operator Q. Unfortunately, since solutions to the PDE at each time t must exist in this subspace X, the derivative of our Lyapunov function here needs to be negative semi-definite only for u within this space X. But we can't really numerically enforce negativity of operators only on some subspace X defined by boundary conditions. So to resolve this, we can instead convert the PDE to an equivalent partial integral equation or pi representation. So this pi representation still models the evolution of some infinite dimensional function, infinite dimensional vector. So it's still a function of space, but this state now does not have to satisfy any boundary conditions or continuity constraints. Instead, these boundary conditions will be incorporated in the operator t as well as the operator a over here, so that this pi representation is parameterized by two operators. Fortunately, these two operators are now partial integral operators rather than partial differential operators, where this class of partial integral operators is just a subclass of integral operators, which take this form as a function from 0 to s and an integral from s to 1, both defined by these polynomial kernels t1 and t2. So this is useful because since these pi operators are parameterized like polynomials, we can actually represent them numerically. Moreover, if we now parameterize a quadratic Lyapunov function by a pi operator p, then the derivative of this Lyapunov function along the vector field will also be quadratic, and we can actually show that this operator q here is also a partial integral operator, which we can compute explicitly given the operators a, e, and t. So this means that we can also numerically represent this operator q. And moreover, we can actually enforce negativity of this operator as a linear matrix inequality. So this means that we can test for existence of such a quadratic Lyapunov functional by solving LMI constraints, which we can do using interior point methods. Now, it has been shown that for a broad class of linear 1D PDEs, we can construct an equivalent partial integral equation representation, at which point we can apply this framework here to test stability of the system, as well as design estimators, design controllers, and solve a variety of other problems, all of which can be done numerically. So in this manner, we have a universal and automatable framework for stability analysis of this class of linear 1D PDEs. The question that we want to answer now is whether we can extend this to also cover nonlinear PDEs. In particular, how can we develop such a framework, such a universal and automatable framework for stability analysis of nonlinear PDEs? And specifically, we will attempt to replicate the SOS framework, which has already been developed for ordinary differential equations. So we'll first cover what this SOS framework actually looks like for ODEs. Then we will go into more details on how this SOS framework actually works for ODEs, and in particular, what it is about polynomials that allows us to perform this SOS program. Then we will replicate the SOS framework for infinite dimensional systems, finding a class of polynomials on infinite dimensional variables. And finally, we will use this infinite dimensional SOS framework to test stability of nonlinear PDEs by first converting them to partial integral equations. So we're going to start with this overview of the SOS framework for ordinary differential equations. So as noted, to test stability of a linear ordinary differential equation, we have this automatable and universal framework in terms of these linear matrix inequalities. However, we can actually generalize that somewhat to the case where the vector field is polynomial. So if the vector field f is polynomial, and we choose our Lyapunov function phi to be polynomial as well, then the derivative of this Lyapunov function along the vector field will also be polynomial. And this is good news because polynomials can be represented numerically. So then, to test stability of our ordinary differential equation, we can pose this problem of finding a Lyapunov function as a polynomial optimization problem. So that is, we have these equality and inequality constraints on polynomial function. Unfortunately, solving such polynomial optimization problems is NP hard in general. And in particular, we don't have an efficient method for enforcing negativity of these polynomials. So instead, we will tighten these positivity and negativity constraints to sum of squares constraints. So we say here that a function v is sum of squares, or SOS, writing that it is an element of this set sigma s, if it is a sum of squares of polynomials. Now clearly then, if v is sum of squares, then it is polynomial, and it is non-negative. That is, it assumes a non-negative value for any value of this variable x. So then we can tighten these positivity and negativity constraints in our polynomial optimization problem here to these sum of squares constraints, meaning that we can test for existence of a Lyapunov function by solving an SOS program or SOSP. And these SOSPs can actually be solved in polynomial time. And in particular, as I will show later on, we can convert these SOS programs to semi-definite programs, which we can then solve using interior point methods. Now, this whole process of converting an SOS problem to an SDP and then solving that SDP has been fully automated. And in particular, a variety of toolboxes have been developed to aid users in doing so. Namely, we have these SOS parsers such as SOS tools, which allow users to declare an SOS program, convert this SOS program to an SDP for the user, pass this SDP to a solver such as Sudumi, and then take the solved SDP and convert it back into a solved SOS program. So really all the user needs to do is to declare an SOS program, and then these parsers and solvers can do the rest. So then, again, we have a universal and automatable framework for stability analysis of ordinary differential equations with polynomial vector fields, or polynomial PDEs. Now note that this SOS framework can also be applied for a variety of other analysis problems, and perhaps even control, but for this presentation, we will focus on just stability analysis. The question then is, can we also use this SOS to test stability of PDEs? Well, by far the most common approach to analyze PDEs is to just discretize them and approximate them by an ordinary differential equation. So for example, if we have a nonlinear PDE, such as this simple Burger's equation here, we see that we have a nonlinear term over here, then we can approximate our infinite dimension state u here at each time t by some finite vector u by evaluating the state at these discrete points spaced delta s dot. Now, this is just a finite difference discretization approach, which is far from the most sophisticated method, but is just for illustration purposes. So then approximating our PDE state by an ODE state, we can also approximate our partial differential equation by an ordinary differential equation, at which point we can test stability using our SOS framework. Unfortunately, doing so, this ODE, of course, only offers an approximation of our PDE. So that means that even if we can verify stability of this ordinary differential equation using SOS, we will still need to perform some ad hoc analysis to make sure that this indeed proves stability of our original PDE. Moreover, the accuracy of this ODE approximation will depend on the number of state variables n that we use in our discretization. But then the complexity, the computational complexity of the resulting SOS program will scale as n plus d factorial squared, where d is the degree of the monomials we use in the SOS program. So then in order to get an accurate ODE approximation, we will need to use a large number of state variables n, but then the resulting SOS program quickly becomes computationally intractable. So clearly, this is not the ideal approach to performing SOS or to analyzing stability of PDEs using SOS. So what we want to do is to instead develop an SOS framework directly for the PDE itself, so without any discretization. In particular, this SOS framework should be universal. It should apply to any polynomial PDE, or at least a class of polynomial PDEs. It should be rigorous, it should not involve any discretization or approximation of the system, and it should be automatable. We should be able to develop software tools to do most of the work for us. Of course, in order to build such a framework for analysis of PDEs, we must first understand the SOS framework for ordinary differential equations. So that will be the focus of the next few slides. Understanding the SOS framework for polynomial ODEs, and in particular, understanding what it is about these polynomials that allows us to perform SOS programming. And for this, let us consider a very simple SOS program. Namely, instead of looking for a Lyapunov function, let us fix a polynomial function v, such as this energy function, so that the level sets here will be just circular. And then let us check whether this function decreases along the vector field f, along the polynomial vector field f. So we can pose this as an SOS program, where our decision variable is a function h, where we require that this function h is equal to the negative derivative of our Lyapunov function along the vector field, and that this function h here is a sum of squares polynomial, so that it is positive semi-definite, and thus this negative derivative is also positive semi-definite. Now, in order to implement and solve this SOS program, of course, we need to be able to solve certain problems. In particular, we need to be able to perform algebraic operations so that we can compute the derivative of our Lyapunov function along the vector field. We need to be able to enforce equality constraints so that we can enforce equality of our derivative to this function h. And we need to be able to enforce positivity constraints. In particular, we need to be able to enforce positivity of this function h, namely that it is a sum of squares function. All of this is possible because the functions v and f are polynomial. I've been using the term polynomial quite a bit now. Let me make it a little bit more concrete. I will say that a function is a polynomial if it is a linear combination of monomials. And in turn, a monomial in some vector x is any product of elements of this vector. Now, given then this notion of polynomials, we can identify three key properties of these polynomials that allow us to solve and implement these SOS programs. In particular, polynomials form a multiplicative algebra, which allows us to perform these algebraic operations. Polynomials admit a unique linear representation, which allows us to enforce these equality constraints. And polynomials admit a quadratic representation, which allows us to enforce these positivity constraints. And I will go into a bit more detail on each of these three key properties next, starting with this first property. Polynomials form a multiplicative algebra. So that means that for any two polynomial functions, p1 and p2, their sum as well as their product will be polynomials as well. So this means that if we have a polynomial vector field and we choose our Lyapunov function to be polynomial, this ensures that the derivative of this Lyapunov function along the vector field will also be polynomial. Moreover, this actually ensures that a sum of squares of polynomials is again a polynomial function, so that we can parameterize this subclass of polynomials, namely a subclass of positive semi-definite polynomials. So then to enforce negativity of this derivative of our Lyapunov function, we can introduce another squares polynomial h and just enforce equality of our negative derivative to this function h. Of course, this leaves the question of how we can enforce equality of these polynomials, which brings us to the next key property, namely polynomials admit a unique linear representation. That is, for any polynomial function p, we can identify a basis of monomials z, as well as a vector of coefficients c, such that we can express this polynomial as a linear combination of monomials. Now note that this representation is unique. So that means that for any two polynomials, p1 and p2, defined in terms of the same basis of monomials, these two polynomials will be equal if and only if their associated coefficients will be equal. So this allows us to represent these polynomials numerically in terms of just their coefficients. Moreover, we can then enforce equality of these polynomials numerically by enforcing equality of the coefficients. And in this representation, we can also actually perform addition of these polynomials by taking the sum of the associated coefficients. Moreover, we can actually perform multiplication in the linear representation as well. So in particular, if we have two polynomials, p1 and p2, defined by these coefficients c1 and c2, then the products of these polynomials can be represented in terms of the Kronecker product of their coefficients and the Kronecker product of these monomials, where this Kronecker product of two vectors just includes all combinations of elements of that vector. Now note here that if this function vector zd here contains all monomials of degree at most d in x, then the Kronecker product of this vector with itself will include monomials of degree at most 2d in x. And indeed, we can actually express this Kronecker product of the vector of monomials with itself in terms of the vector of monomials of degree at most 2d in x using some matrix M, where this matrix can be computed explicitly. We know how to compute this matrix. So in this manner, we can actually express this product of these two polynomials in terms of this higher degree monomial basis in the linear representation, where we can compute the coefficients defining this product in the linear representation exactly. And moreover, we can compute them numerically, right? This Kronecker product and matrix vector multiplication can all be performed by a computer. So then we can also numerically compute the derivative of our Lyapunov function v along the vector field, as well as enforce equality of this derivative to polynomial function h by enforcing equality of the coefficients in the linear representation. Now all this leaves then is to enforce positivity of this polynomial function h, which brings us to the last key property, namely polynomials admit a quadratic representation. That is, for any polynomial function v, we can express it in terms of this pseudo-quadratic format here using a matrix P. Moreover, the function v will then be a sum of squares polynomial if and only if this matrix P here is positive semi-definite. So this means that we can parameterize a class of positive semi-definite polynomials, namely these sum of squares polynomials, by positive semi-definite matrices, and thus we can enforce SOS constraints as LMI constraints. For example, if we want to enforce this SOS constraint, that h here be a sum of squares function, then we can parameterize h here in the quadratic representation by some matrix Q, and then we can enforce positivity of this matrix Q as an LMI constraint to ensure that h is indeed a sum of squares polynomial. Now, unfortunately, the quadratic representation is not in fact unique, so there may be different matrices P which define the same function V, but we can convert from the quadratic representation to the linear representation. So if we have some polynomial in the quadratic representation defined by some matrix P and these monomials of degree D, we can represent this equivalently in the linear representation using now monomials of degree at most 2D, and where this vector of coefficients C here can again be computed exactly. In particular, this matrix A and this vectorization of the matrix P can both be computed exactly and numerically. So then we can enforce equality constraints of polynomials in this linear representation, meaning that we can actually pose our SOS program here as a semi-definite program, or SDP. So for example, if we have our SOS program here, we require h to be a sum of squares polynomial, and we require this function h to be equal to this negative derivative of our Lyapunov function, then we can parameterize our function h here in the quadratic representation by some matrix decision variable q, and we can compute the coefficients c defining the derivative in the linear representation. And then to enforce positivity of h, we enforce positivity of our decision variable q here, this matrix q. And then to enforce equality of these polynomials, we enforce equality of the coefficients defining them in the linear representation. So in this manner, we can formulate our SOS program as a semi-definite program, which we can then solve numerically. So these three key properties, namely that polynomials form a multiplicative algebra, that they emit a quadratic representation, and that they emit a linear representation, these three key properties are really at the basis of every SOS program, including for stability analysis, but also for other applications for these linear differential equations. Question then is, how can we replicate this for partial differential equations? So that will be the focus of the next few slides, replicating the SOS framework for infinite dimensional systems. We will focus here on just nonlinear 1D scalar valued PDEs. So for example, consider again Burger's equation, which is a stable system, as the simulation here shows. Now we note that in this system, of course, the state u at each time t is still a function of space. So we can test stability by looking for a Lyapunov function, but then this function must in fact be a functional, meaning that it maps a function to a scalar value. So then in order to perform SOS programming in this setting, we have to define a class of polynomial functionals, mapping functions to scalars. So how can we do that? Well, the obvious approach is to just take an integral of pointwise polynomial combinations of the function u and its spatial derivatives. So for example, we can evaluate the function u and its spatial derivatives at some point s in the domain, take a polynomial combination of the resulting scalar values, and then just integrate that polynomial over the domain 0 to 1. So clearly, this will be a map from our function space to a scalar value, and it does appear to be polynomial. And in fact, using such a pointwise polynomial functional, we can certify stability of Burger's equation, in particular just taking this integral of the state u squared at each point s in the domain. Unfortunately, this class of functionals fails our key properties of polynomials that we identified for ordinary differential equations. In particular, the state u and its spatial derivatives are not independent, meaning that this representation of these functionals may not be unique, and this class of functionals does not define a multiplicative algebra. So for example, if we take the product of this functional v with itself, so if we take the square of this function, then the result will be expressed as a double integral on these variables s and theta. And there is no way that we can express that as just a single integral of some pointwise polynomial combination of the state u or its derivatives. So this class of functionals we define here is not closed under multiplication operations, which will be problematic if we try to implement this numerically. So this is not the right way to define polynomials in an infinite dimensional setting. So then how do we define polynomials on these function valued variables v, or these distributed states, as we may refer to them? Now, of course, this class of polynomials has to satisfy our key properties, namely, we must have a unique linear representation, it must define a multiplicative algebra, and we must have a quadratic representation if we're going to be performing this SOS program. So let us start with this first property, namely this linear representation. So in the finite dimensional setting, a polynomial is just a linear combination of monomials. So then how do we define monomials on such an infinite dimensional vector v? Well, for this, again, let us take a step back to the finite dimensional case. So if we have a vector x of variables, of n variables, then the monomials of degree 1 in this vector x will include just the variables x1 through xn themselves. So this will just be the vector x. Similarly, the monomials of degree 2 will include all products xi times xj for I and j both ranging from 1 up till n. So this will be a vector of n squared elements. The monomials of degree 3 then include all products xi times xj times xk for I, j, and k ranging from 1 up until n. So this will be a vector of n cubed elements. Moving now to the infinite dimensional setting, where our vector v becomes a function, we note that our discrete index I here now becomes a continuous variable. So then the monomials of degree 1 in v will be the function v at each point s in 0 to 1. So that will just be the function v itself. The monomials of degree 2 then will become all products v at s times v at theta for s and theta both ranging over the domain 0 to 1. So this will be a function of 2 spatial variables. Similarly, the monomials of degree 3 will become the products v at s times v at theta times v at eta for s, theta, and eta over the domain 0 to 1. So this will be a function of 3 spatial variables. So note then that in this infinite dimensional setting, the domain takes the place of the dimension. That is, whereas in the finite dimensional setting, the monomials of degree 3 will be a vector of n cubed elements, so it will be a larger vector. In the infinite dimensional setting, the monomials of degree 3 are still a scalar valued function, just a function of 3 spatial variables. So the domain takes the place of the dimension. So then how do we represent these monomials of arbitrary? Well, in the finite dimensional setting, to represent this product of xi times xj for all I and j in 1 to n, we can use this Kronecker product of the vector x with itself. In the infinite dimensional setting, we can do the same thing. So in particular, for a function in k variables and a function u in l variables, we define their tensor products to be a function of k plus l variables, so that v tensor product with u at s1 through sk and theta1 through theta l will be just v at s1 through sk times u at theta1 through theta. So for example, if we just take the tensor product of v with itself, then the result will be a function of 2 spatial variables, namely v at s times v at theta for s and theta over the domain 0 to 1. So using this tensor product, we can also define our degree d monomial in v as this d-th order tensor product of the function v with itself, which will be a function of d spatial variables. Now we will refer to this monomial as the degree d distributed monomial in v to distinguish it from the pointwise monomial combination of v with itself. So given then these distributed monomials, we can define a distributed monomial basis as including all these monomials from degree 1 up until degree d in the function v. So this will include functions in one variable up until functions in d spatial variables. Now one quick note here. In the finite dimensional setting, of course, if we take the tensor product of x with itself, then this result will include both the product x1 times x2 and the product x2 times x1. Whereas we really need to include only one of these if we want to have a proper basis. So we should really be taking only unique combinations from this Kronecker product. Similarly, in the infinite dimensional setting, we should really only be taking unique combinations of this tensor product. So for example, v at s times v at theta for s ranging from 0 to 1, but now theta ranging only from s until 1. Now, I will not be doing so throughout the presentation, as it will complicate the notation, but keep in mind that all results we present here can be adapted to account for this uniqueness as well. Okay, so now we defined our basis of distributed monomials. How then do we define a distributed polynomial on our function v? Well, again, a polynomial is just a linear combination of monomials. So we need to define a class of linear operators acting on our monomial basis. And for this, we have the Riesz representation theorem, which tells us that any bounded linear map from a square integrable function in d variables to the scalar value can be expressed as an integral, as d integrals, with some function k here, this kernel k, itself being a square integrable function in d variables as well. So we can parameterize a class of linear operators acting on our degree d distributed monomial, so acting on this space of functions in d variables, using these kernels k, which are themselves square integral functions in the spatial variables. And we will denote the associated integral operator corresponding to this kernel k as this small integral given by k. Using then this class of linear operators, we define a notion of distributed polynomials, where we say that this function p mapping a scalar valued 1D function to a scalar is a distributed polynomial if it admits a decomposition of this form. So if we can express it as a sum of these distributed monomials acted upon by these integral operators, where these kernels ki are functions in I spatial variables. And we will denote this set of distributed polynomials as this R in V. Okay, so then we have this class of distributed polynomials. We note that as an example, we have a cubic polynomial over here, where you have the linear distributed monomial, the quadratic distributed monomial, and the cubic distributed monomial acted upon by a single integral, a double integral, and a triple integral, where these functions, these kernels, are functions of one variable, b is a function of two variable, and c is a function of three variables. Now note also that in this case, we actually choose a, b, and c here to themselves be finite dimensional polynomials. So polynomials in just a finite number of variables. And in fact, we can parameterize a subclass of distributed polynomials by choosing these kernel functions k here to themselves be polynomials in just a finite number of variables. So this will be a subclass of distributed polynomials, which we can then represent numerically, since again, these finite polynomials can be represented exactly numerically. Okay, so then we have our class of distributed polynomials. We have the linear representation of these distributed polynomials. Do these distributed polynomials also satisfy our key properties? In particular, do they form a multiplicative algebra? And the answer to that is yes. If we have any two of these distributed polynomials, then their sum in their product will be distributed polynomials as well. And in fact, we can exactly compute the coefficients or the kernel functions defining the resulting sums and products of these polynomials. So for example, if we have a linear polynomial P1, so involving only the linear distributed monomial, and another linear polynomial P2, so again, involving only the linear distributed monomial, then the sum of these two polynomials is again a linear distributed polynomial, where the coefficients are now defined by the sum of the coefficients a and b, defining P1 and P2. Similarly, if we take the product of these two polynomials, then the result will of course be a quadratic distributed polynomial, where now the coefficients are defined by this tensor product of the functions a and b. Okay, so these polynomials form a multiplicative algebra. That then leaves the third key property, a quadratic representation. So in the finite dimensional case, a quadratic representation is defined by taking inner product weighted by some matrix P. So in the infinite dimensional setting, we will do the same thing. We define this quadratic representation by taking an L2 inner product weighted by an operator P. And in particular, we will choose these operators P to be integral operators. So we define here this operator P mapping a function in L variables to a function in K variables by basically just integrating out the dependence on this variable theta in L dimensional domain and introducing a dependence on this variable S in the K dimensional domain. So then this operator will map a function in L variables to a function in K variables. And this will be the integral operator associated to this kernel R, where R is now a function of K plus L spatial variables. So given this class of integral operators, then we can parameterize a quadratic representation for these distributed polynomials by taking an inner product of our distributed monomial basis weighted by an operator P, where each of these components P map a function in multiple variables to a function in another set of variables. So for example, P1D here maps a function in D variables to a function in just one variables, so that we have a suitable inner product here. Now we will also parameterize a class of sum of squares, or SOS distributed polynomials then, by requiring this operator P defining the quadratic representation to be positive semi-definite. So then clearly, if V is a sum of squares distributed polynomial, then V will be positive semi-definite. So that we've parameterized a class of positive semi-definite distributed polynomials by positive semi-definite operators, which in turn we can parameterize by positive semi-definite matrices. Okay, of course, again, the quadratic representation is not unique, but we can convert from the quadratic representation to the linear representation in this infinite dimensional set as well. In particular, if we have such an integral operator mapping a function in L variables to a function in K variables, we can define the associated vectorization of this operator as the integral associated to the kernel R. So this integral will map a function in K plus L variables to just a scalar value. So given this vectorization of the operator, then we can convert from this quadratic representation involving the inner product of the distributed monomials of degree k and the distributed monomials of degree L to a linear representation involving the distributed monomials of degree k plus L. Given then this vectorization of these integral operators, we can define a vectorization of a matrix valued operator by just taking the concatenation of these vectorizations of these scalar valued integral operators. And then, given this vectorization, we can again convert from the quadratic representation to the linear representation. So if we have a function v here, a distributed polynomial in the quadratic representation defined by this integral operator p, we can define an associated operator c to represent this function in the linear representation, now using, of course, monomials of a higher degree 2D. And again, these coefficients c can be computed exactly and numerically. So in this manner, we've defined a class of distributed polynomials that satisfy all our key properties, namely we have a linear representation, they form a multiplicative algebra, and we have a quadratic representation. So then we should have all the tools we need to perform sum of squares programming on these infinite dimensional vectors V. Unfortunately, PDEs in general are not represented in terms of such distributed polynomials, which brings us to the last part of the talk. How can we actually test stability of these PDEs using sum of squares programming? In particular, we will have to convert these PDEs to the pi representation. So if we consider a general polynomial PDE, these polynomial PDEs are in general represented using pointwise polynomial combinations of the state u and its spatial derivatives. So we take a combination, we evaluate these states at some spatial position s, and then we just take polynomial combinations of the resulting scalar values. So for example, Berger's equation here involves such a pointwise product of u and its first order spatial derivative. So this is unfortunate since, of course, this pointwise polynomial is not the same as our distributed class of polynomials that we defined previously. In addition, the state u in the PDE representation at each time t exists in this subspace x, and this subspace x constrained by these boundary conditions is a proper subspace of L2, of the space of square functions. So our distributed polynomials, of course, were defined on L2. So if we're going to be applying our SOS framework to these PDEs, we must first convert them to a representation in terms of distributed polynomials on L2. And for this, we will use the partial integral equation representation. So again, we define this class of partial integral or pi operators here, mapping a function in one variable to a function in one variable, using these integrals from 0 to s and an integral from s to 1, both parameterized by these polynomial functions r1 and r2. So these finite dimensional polynomial functions r1 and r2. And we will denote this set of pi operators as pi subscript 2. Now, given this class of pi operators, it has been shown that if we consider just the space x of second order differentiable functions, then under sufficient linear boundary conditions, so if x is defined by sufficient linear boundary conditions, we can actually define pi operators t and r, such that we can express u as well as its first order spatial derivative in terms of the second order spatial derivative of the function u, using these pi operators. So using these operators t and r, then we can actually represent a linear PDE on this state u in the domain X as a partial integral equation on the fundamental state corresponding to the second order derivative of u, which will just be an element of L2. This second order derivative of the state will not need to satisfy any boundary conditions or continuity constraints. So all of this has already been proven for the linear setting. We will now exploit this technology in the nonlinear setting. So if we have now a nonlinear PDE defined as such a pointwise polynomial combination of the state and its spatial derivatives, where we assume that the set X here is defined by sufficient linear boundary conditions, then we can define these operators t and r to express u and its spatial derivative in terms of the second order spatial derivative. So then using this relation, we can express u here in terms of this fundamental state v, corresponding to the second order derivative of u. We can also express this first order derivative of u in terms of the fundamental state, and we can express this second order derivative of u in terms of the fundamental state, namely, this will be the fundamental state. Where again, this fundamental state v here does not have to satisfy any boundary conditions or continuity constraints. Of course, this is just for second order PDEs, so assuming the state here to be only second order differentiable, but we can in fact generalize all of this to higher order PDEs as well by taking the fundamental state to be the highest order spatial derivative of the PDE state. So with that then, we have an equivalent pi representation of our nonlinear PDE expressed in terms of this fundamental state and using these pi operators t and r. But unfortunately, this representation is still expressed in terms of pointwise polynomial combinations, whereas our distributed polynomials are, of course, expressed in terms of these distributed monomials. So then how do we express this pi representation in terms of our distributed monomial basis? Well, for this, recall that our distributed monomials are given as these tensor products of the state v with itself. But then this div-ordered tensor product will be a function of d spatial variables. So then in order to represent a pi representation in terms of such distributed polynomials, but only mapping the dynamics of a function in one variable, we need to parameterize a class of operators mapping a function in d variables to a function in just one variable. Now, there are several classes of multivariate pi operators we can consider. If we restrict our attention to just d is equal to 2, we define this class of tensor pi operators here. This class of operators mapping a function in two variables to a function in one variable using these nested integrals. So 0 to s, 0 to theta, s to 1, 0 to s, and s to 1, s to theta. So this class of tensor pi operators is parameterized by these three finite dimensional polynomials b1, b2, and b3. And we will denote this class of tensor pi operators as pi 2 to the power of tensor 2, where this tensor 2 indicates that we're mapping a function in two variables to a function in just one variable. Now, why do we define this class of pi operators in this format? And in particular, why do we call them tensor pi operators? Well, because we can actually define a notion of the tensor product of two pi operators. So if we have two standard pi operators, p and q, mapping a function in one variable to a function in one variable, we can define a notion of the tensor product of these operators as a tensor pi operator, where this tensor product is such that the product of p applied to v with q applied to v can be expressed as the tensor product of p and q applied to the tensor product of v with itself, where we can explicitly compute this tensor product of these pi operators. So we can explicitly compute the parameters defining this tensor pi operator. So using this result, then, we can express these pointwise quadratic functions, such as t applied to v squared or t applied to v multiplied with r applied to v, using our distributed quadratic monomial, so the tensor product of v with itself. So then if we have a quadratic partial differential equation, involving these linear terms in the state and these pointwise quadratic terms in the state and its first order spatial derivative, we can represent this equivalently as this partial integral equation, where, for example, we represent here this product of u with its first order derivative using the tensor product of t and r applied to this degree 2 quadratic distributed monomial in our state v. Now here the operator A will be just a pi operator, and the operator B will be a tensor pi operator. And then we have a quadratic pi representation for our PDE expressed in terms of our distributed monomials. More generally, if we have a nth order quadratic PDE, so still just involving quadratic combinations, but now an nth order derivative of our state u, we can represent this equivalently as a quadratic pi. We're now expressed in terms of our distributed monomial combinations of v with itself, and where a will be a pi operator and b will be a tensor pi operator. And we can prove that these two representations are equivalent. So if u satisfies our quadratic PDE, then its highest order spatial derivative will satisfy the pi. And moreover, if v is a solution to our quadratic pi, then t applied to v will be a solution to the quadratic PDE. So given that this quadratic pi representation of our quadratic PDE expressed using our distributed monomial basis, we can finally perform our SOS programming to test stability. So in particular, we can parameterize a quadratic Lyapunov functional by a pi operator. And then the derivative of this Lyapunov functional along the vector field will take this form here in terms of this L inner product and expressed in terms of our distributed monomials. And then we can enforce negativity of this derivative by requiring it to be equal to this negative semi-definite function over here. So then if there exists a positive semi-definite operator P and positive semi-definite operator Q such that this condition here is satisfied, such as this equality constraint here is satisfied, then this actually proves exponential stability of our pi. In particular, it shows that the norm of the L2 norm of the state at each time t is bounded by the L2 norm of the initial state multiplied with an exponentially decaying function with exponential decay rate alpha. Now note here that although all of this is expressed in terms of the pi representation, t applied to v here actually corresponds to our PDE state. So although we're testing stability in the pi representation, we're actually verifying stability of solutions to the original PDE. Moreover, note that we can also generalize to higher degree monomials. So for example, if we have a vector field involving higher degree monomial basis, but we can also use a functional v using higher degree monomials as well, although so far our implementation has been limited to only quadratic Lyapunov functionals and quadratic vector fields. So does all of this work? Well, we have some numerical examples to illustrate. In particular, let us first consider again Berger's equation, but we added here a reaction term scaled by this parameter r. We can construct an equivalent pi representation of this form here, where these operators t and r are defined here explicitly. And then using distributed SOS, we can verify stability up to this value of 9.8696. And if we test this analytically, using thus this energy functional, we can similarly verify stability up to r is pi squared, which gives us the same value here. So this indicates that our SOS result is probably tight. And indeed, if we simulate solutions to the system for just r is equal to 9 here, and starting with this cosine function over here, we note that solutions do indeed decay to 0 exponentially. So that if we plot the L2 norm of the solution, we find that it exhibits this exponential decay. And in fact, the rate of decay that we are able to verify with our SOS programming appears to be quite tight for this case, at least for this initial condition. Now, the second example, we consider the Korteweg-de Vries equation, which is a third order PDE. And we've added here another quadratic term scaled by this parameter r. So we're just taking the product of u with itself scaled with this parameter r to make the system a little more interesting. Then we can construct an equivalent pi representation. And then again, we can apply our distributed SOS framework to analyze stability. And we were able to verify stability up to a value of R of 4.6098. Now, analytically, we were only able to verify stability up to 4.0017. So clearly that result there is conservative. And indeed, if we simulate solutions for values are larger than this 4.0017, for example, if we take R is 4.6, we find that solutions do indeed still converge to zero. And in fact, they do so very rapidly. You can see here the time scale is very small. And in particular, we were able to verify stability with a rate of decay of 32, almost 32. And even this rate of decay does not appear to be tight, at least for this particular initial condition. So it's possible that using a higher degree Lyapunov functional, we may be able to verify a tighter, higher degree of exponential stability as well. Although, of course, it is also possible that there are other initial conditions for which this rate of decay is in fact tight. And as a final example, we consider a fourth order PDE, namely the Kuramoto-Sivashinsky equation, where again we add this quadratic term scaled by this parameter r. We can construct the equivalent pi representation, and then we were able to verify stability up to a value of r of 0.7202. Whereas analytically, we will only be able to verify stability up to 0.3608. So again, that appears to be quite conservative. And indeed, if we simulate for example, r is equal to 0.7, solutions again converge to zero very quickly, an even smaller time scale over here. And indeed, we found that we can verify exponential stability with a rate of 408, which appears to be relatively tight, at least for this choice of initial condition and simulated solution. So that brings us to the end of the talk. Overview here. We've known that we defined this class of distributed polynomials by taking tensor product of this infinite dimensional vector with itself. Using this class of distributed polynomials, then, we can express our PDEs, our nonlinear or at least quadratic PDEs, in equivalent format as quadratic pi's using such distributed polynomials. And then given this quadratic pi representation, we can verify stability using sum of squares in terms of, again, these distributed polynomials. Now, of course, we've only actually considered 1D systems, scalar valued, global stability. So there's a lot more that can be done here. In particular, I think a next step would be to consider higher degree Lyapunov functionals. We've only used quadratic Lyapunov functionals, but perhaps tighter results can be obtained using, for example, quartic Lyapunov functionals. But that means we have to parameterize another class of multivariate pi operators. Also, nonlinear systems are generally not globally stable. That's quite rare. So we want to be able to test local stability as well, perhaps derive some positive standard results. It would be interesting if we could apply to coupled PDEs. This notion of these distributed polynomials generalizes quite easily to that case, but the computational complexity will, of course, increase. PDEs in multiple spatial variables would be interesting, but again, computational complexity will increase in that setting as well. And there are other applications of SOS programming that we haven't even considered here, such as computing upper bounds on the long-time mean energy of PDE solutions, which would be an interesting application to consider as well. Ultimately, of course, we would like to develop a general software suite for analysis of PDEs using sum squares programming. Akin to this PyTool software suite, which has been developed for linear PDEs, but that will be for future work. For now, I would like to thank you for your attention, and if you have any questions, feel free to reach out to us via email. Thank you.